Hello everyone, myself Dr. Sriparna Shaha, and currently on my YouTube channel we are talking for the playlist on lectures on artificial intelligence. In the last video we have talked about different search techniques, and in that particular video we have given you the introductory concepts that you will be required to learn the different search techniques that can be uninformed search techniques or the informed search techniques. Today we are going to talk about much detailed view or the much deep down approach of each of the search techniques that belongs to the blind search techniques. And the first search technique that today we are going to talk about, that is the breadth first search. So for these particular search techniques, what we need to know first, the concept of fringe. So fringe is what, where we are going to store the new nodes, that is the unexplored nodes that will be stored in the fringe. So for the breadth first strategy, that is in the row wise, basically breadth means we are going in the breadth, right? So what is the breadth? So will be searching the tree in this region, right? So if in this form we are going to, that is along the breadth, we'll be searching. Now new nodes will be generated, that are the unexplored nodes that will be stored in the fringe. So for this particular tree, what is the fringe initially? So here we have searching this particular node, that is the node number 1. So node number 1 will be currently in the fringe, right? This is in the fringe. Now whenever we'll be searching the one particular node, so the children of that node that belongs to the unexplored set. So this is the unexplored set that we need to explode currently. Now after this node 1, where we can go in the breadth for search technique, that is we can go in the node 2 and 3, that are the children. And as it's in the breadth for search technique, we'll be writing the 2 and 3 in the fringe. Now we'll be searching the node 2. So in the node 2, what are the children we are getting? The children 4 and 5. And each time we need to check whether we have reached the goal or not. We haven't reached the goal so far. So now we are going to remove the node number 2. Just check. In the earlier fringe, there are only 2 nodes, 2 and 3. Now after searching the node 2, so 2 will be removed from the fringe and the 4 and 5 will be added to the fringe. And these 4 and 5 are the children of node 2. And where I have written the node number 4 and 5, that is after node number 3, that is the last part of the fringe. So earlier it was 2 and 3. Now upon searching the node number 2, this node will be vanishes out, and the children of that node, that is 4 and 5, those will be added to the fringe, and those addition will be at the last part of the fringe. So now the fringe becomes 3, 4 and 5, and the first node present in the fringe, that will be explored now. So that is the node number 3. So will be exploring the node number 3 now. So 3 will be removed from that fringe. Just check, this was the 3. So 3 will be removed from, and its child nodes, that is child nodes are what? 6 and 7. So 6 and 7 will be placed at the later part of the fringe. So now the fringe becomes 4, 5, 6 and 7. Now we'll be searching at the node number 4. Then we'll be going to the node number 5. Then we'll be going to the node number 6. Then we'll be going to the node number 7. And at any point of time during the searching of each of the node, if we can find out that is this particular node has the goal node, then we are going to stop the searching. Otherwise, we'll go on searching the tree in the breadth first way. Now, we have already talked about to calculate the time and space complexity, we need to know three variables B, D and M, where the B is the branching factor, D is the depth of the shallowest goal node. And this particular search technique is a complete one. And this particular search technique is optimal as the step cost is 1. And the number of nodes are generated for each of the interval, and if we can calculate this, then the time and space complexity becomes order of O, this particular equation or this particular value, where b to the power d plus 1, that based on the order of no O will be a big O notation, that you can calculate time and space complexity of the breadth first search technique. So this was one example of breadth first search. Now how this search technique will go on? This search technique will go on from this start node. Then it will be in the breadth first way. So it will search this node whether it is the goal node or not. Then it will search this particular node whether it's a goal node or not. Then this search technique whether it's a goal node or not. Next, these children or this node will be searched. Then after that this. So these will be searched, then these and these. So this way it will go on searching along the breadth way, and your goal is present over here. So if you could have searched in this particular way, then you can find the goal node. And the breadth first search will go on from here to here to here to here, then here. This way the breadth first search technique will go on and the search will stop when it finds the goal node. Okay. So this is the BFS. So what we have learned from the BFS search technique, that is the memory requirements are a bigger problem for breadth first search technique than the execution time. And the exponential complexity search problem, that is the problem where the search problems are increasing in an exponential way, that cannot be solved by uninformed methods for any but the smallest instances. So if the tree is in a smaller one, so we can solve it using the uninformed method. But if it is an exponentially growing tree, so it will be difficult to solve using BFS. Next search technique that we are going to talk about, that is the uniform search or uniform cost search. So this will be in the similar fashion of breadth first search. Same idea as the algorithm for breadth first search, but it will expand the least cost unexpanded node. Here the FIFO, so first in first out, that Q that we have taken for the BFS, that will be ordered by the cost. Here the equivalent to regular BFS if all costs are equal. So if all the step costs are equal, then it will be equivalent to BFS. If the all step costs are not equal, then the FIFO Q will be ordered by the cost. So this is the uniform cost search. Now let us have one example. And this particular figure has been taken from the book by Russell and Norvig. This is a very famous book, and I will always tell you to go to read any good books to understand the concept in a much deeper way. So you can go to this book by the authors Russell and Norvig. The book name is Artificial Intelligence. In this book, you can find this root finding problem that has been solved using uniform cost search. So the root finding problem is that is different cities are there basically, and between the cities the cost between traveling from this city to this city, that is given by this. So cost, that is the travel cost from city A to city B, is 5. So in this way you can design the root finding problem. And so this is that is the A figure is the state space showing the cost for each operator. And in the B figure, that is this particular is the division between A figure and the B figure. And in this B figure, what we can see, that is the progression of the search, how the searching is going on. So how the searching? So first in the fringe it will be only the S node, and the S node, that is the travel cost between S to S, obviously the value will be 0. You are in one particular position, so you are again coming to this particular position, that means you are not moving, so the value is 0. Now from S, what are the children are available in the root? That is A, B and C. So and the cost from S to A is 1. Just check over here. S to B is 5 from here, and S to C is 15. This value, right? Now this will be the child nodes. Now after the child node, it will expand which node? Where the path cost value is lowest, and the path cost value is lowest for A node, so it will expand A node and finds it that its value is 11. So 11 value. So next it will go on, and this will expand the node that is between B and C, and here the B value, the cost value is lower, so B will be expanded, and from B again it can go to the value G. And why the value is, just check over here, why the value is here 10, the value is 10, just let me just erase. Okay, so the just let me explain for 11 also. So between S and A the value is 1, and A to G is 10, so it is 1 plus 10, so it becomes 11. Now why it becomes 10? So S to B, just a second, so S to B the value is 5, and B to G the value is again 5, so we are moving in this fashion, so it is 5, so this value become 10. So now what will happen for the uniform cost search? It will check between these nodes, and whichever has the lower path cost, it will expand that node. This is how it goes on. Okay, so this is the uniform cost search. So it is a complete if the cost is greater than the some threshold, and the step cost will be greater than equal to epsilon, and epsilon value is greater than 0. Now the time complexity, so it cannot be that much easily defined, as here there is another factor involved, that is the path cost. That value is not equal every time. So to calculate this we need this C star value. Now the space complexity you can again calculate by having this C star value, and this particular search technique is an optimal one, as here the nodes are expanded in increasing order, right? So this is the uniform cost search. The next search technique today we are going to talk about, that is the depth first search. So earlier it was the breadth first search. So how breadth first search was there? One particular node have been removed, and its children value has been placed at the later part of the last part of the fringe. That was for the BFS. Currently we are talking about DFS, depth first search. Now just check. So first the fringe value will be 1. Now the fringe value will be the children of 1, so that is 2 and 3. That is similar to BFS. Now 2 is at the first position of the fringe, right? 2 is in the first position. So obviously now 2 will be expanded. So 2 we are expanding. So we are going to get 4 and 5. Now just check. So it was 2 and 3 earlier scenario, right? Now 2 has been expanded. So 2 have been removed. But the children of 2, that is 4 and 5, that has been placed at the first position of the fringe. Not like BFS, where the nodes have been placed at the last position, but here the nodes have been placed as the first position of the fringe. So now the fringe becomes 4, 5 and 3. Now as the nodes fringe is now 4, 5 and 3, you need to expand node number 4. Now 4, then this way. Now this node will be expanded. Now 5 will be expanded. Now these nodes are the children, then these, then these. Then will come up at the 3 node position. Then these 2 children, then these, then these. And why we have stopped? We haven't or we are not exploring the children node of this particular node, so as the goal node is marked as the green. So whenever we are going to obtain the goal node, we are not going to go to expand these nodes, right? So we are not expanding the node over here. So this is the DFS or depth first strategy. Okay, so these nodes are not, or sorry, I must check it in the other way. These nodes, okay, so these particular bubble, these nodes are not basically we are not actually checking these nodes, as we have already obtained the goal node, and the goal node is present over here. This is the goal node that we have already obtained, so we are not going for this. So this is the depth for search. So this search technique is complete for a finite search tree, and this is not optimal, and the time and space complexity you can calculate by the big O notation by the equation. The time complexity, it will be b to the power m, and the space complexity, it will be bm, where the b is the branching factor and m is the maximal depth of a leaf node. By that you can calculate this. Okay. Now on the next video we are going to talk about another variant of DFS or depth first, that is the depth limited strategy. So up to this we are going to stop the particular video. On the next video it will be about DLS or depth limited search technique. So I hope you have liked this particular video, and happy studying.